Oh, I have not shared my screen. Let me share my screen. I hope you can see my screen. Now, welcome to week 12 live session of molecular spectroscopy, a physical chemist perspective. So this is going to be the last discussion session for this semester. In this week's material, what we are going to discuss is so far what we have discussed. So we can sum it up in this uh, using this electromagnetic spectrum maybe. So we have discussed the microwave spectroscopy, that is the part of the this region. So let me use the pointer, the microwave spectroscopy, right? Uh, this part, and then we have so this we deals with the rotational levels. Then we move on to the infrared region, infrared spectroscopy, where we discuss about the vibronic spectroscopy, vibrational normal modes of vibration and all. In between, we have learned the basics of the symmetry, so that we can get help to get the normal modes of vibration, that a particular molecule, how they can be, we can get the normal modes of vibration and which symmetry species they belongs to, that we can understand. And the symmetry and energy goes in hands in hand. So that actually helped us actually understanding the degeneracies and other things. And we are in between also we have learned the Raman spectroscopy, which have both applications during the rotational Raman and vibrational Raman. And we have understood that how Raman spectroscopy is helpful in determination of the bond length of a homonuclear diatomic molecules, and obviously other many other applications are there. And what is the application for means what is the main application? I should not say main application, but what is the application comes to your mind when we say microwave spectroscopy at this point of time? I-
Microwave basically bond strength and basically
Bond strength or bond length?
uh, bond length actually can be determined using this microwave. Yes, microwave.
Yeah.
Yes, you are
So
talking about microwave. Yes,
yes, from
Yes,
infrared,
rotational spectrum.
yes, from infrared you can get the idea about the bond
Bond
strength.
strength.
Yes, right. And then we have discussed the electronic spectroscopy, which mostly constitute from UV to visible part. And UV, so for that, obviously in between we have used, so in this spectrum, while discussing this molecular spectroscopy, we have used quantum mechanics as a main mathematical tool, right? And spectroscopy being a application or uh, uh, that whatever we learned in quantum mechanics, we tried to use that in the spectroscopic part. And then in electronic spectroscopy, we have discussed a benzene, how this absorption spectra looks like and what each peaks are related to. And we have used the help of symmetry there, right? If we could not, if we did not study symmetry, then it would have been very hard to discuss those which band is due to what and why the absorption, or I would say yes, the why the absorption or the molar absorptivity is more for uh, more for a particular band rather than the others. We have learned the um, spin, so orbital selection rules, not exactly the selection rule. We did not derive that, but we have used the orbital overlap theory and sorry, the orbital selection rule. We have used, we have learned the Frank-Condon factor, how they and the spin, if the transition is spin forbidden or not. So up to this part we have discussed, right? So now the next and the ultimate focus was there in the NMR spectroscopy. So NMR spectroscopy is a molecular spectroscopic tool that we chemists actually use day to day. Not maybe us, we are spectroscopist in the sense uh, uh, we use NMR spectroscopy, means for I'm saying on behalf of my lab, but very little. But as compared to to suppose organic chemist or inorganic chemist. They need it on a everyday, day-to-day basis. Whatever molecule they are synthesizing, they need to see if that has formed or not. Even chemical yield can be, or your reaction yield can be monitored through NMR spectroscopy. Like one, suppose you need to form some bond, and suppose some proton or some carbon that is going to vanish. So how much that is thing is there in the reaction mixture or not? From there you can even have the idea that how much of your molecule has formed through a particular process. So basically, we are going to discuss the NMR spectroscopy now. And in NMR spectroscopy, have you done NMR or have you used NMR spectroscopy so far in practical use?
No, I have not used,
Because
but we are planning to do in the use to say that thing we have synthesized. We are planning to use this in this
yes, so to
NMR.
know the purity and the other things, electronics nature of a particular group, you need to get the NMR spectroscopy, right? So in
Yes.
NMR spectroscopy, so far now we are dealing with the excitation of electrons, right? How in rotational level, how the electron is populated. To be honest, we should not say electron here right now. We can, when we discuss about the states, electronic states, so we can say the molecule is populated upon a certain state. So, a electron can be excited from HOMO to LUMO. But
Yes.
then when we discuss in terms of singlet and triplet, there we are actually discussing about the molecule. The molecule is in singlet state or doublet state or triplet state, like that. So here I would say that in this case we are particularly going to focus on the nuclei, not the electrons, to be honest. And we are going to excite the nuclei, and we are going to see if the nuclear spin is going to change or not. And that energy is actually very, very less, even lesser than the microwave spectroscopy. So as you can see from this electromagnetic spectrum, now we are going to discuss this part, a long wavelength, radio wavelength, right? But
Reduce.
a very less energy, very, very low energy. So that we are going to talk about. And I'm not going into the details, but as we already know that for NMR spectroscopy, you need similarly as what some requirement was there for the rotational spectroscopy, vibrational spectroscopy, that regarding the dipole moment and all. So here also it is required that your nuclei should have some nuclear spin, and like those would be NMR active, NMR spectroscopy active, and those kind of molecules are so proton NMR. That is a very commonly used, right? Proton NMR, 13C NMR. Can you tell me why they use 13C, not 12C? Can you guess maybe?
And yes, yeah, that is 13C has the spin is there. In case of 12C, it is all are coupled and total spin is zero. That's why
Yes,
13C is preferred.
yes, 12C. I guess 12C is zero.
Yes.
The nucleus spin is zero. Then what about uh, have you heard of 31P, like
Your opinion,
phosphorus
yes,
NMR?
yes, yes,
Like
yes. That we are
so,
planning to do this
acha, so in
30.
your compound phosphorus is there.
Yes, 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 yes.
Okay. So there are even boron NMRs, so the 11B, 10B, both are, I think, NMR active, but the nuclei spin, I think, is different. So I think most majorly I have done 11B, I guess, if I'm not wrong. Okay. And from there, I guess you can understand 11B, I think, is going to be something like 3 by 2, the nuclear spin, something like that. I'm not sure at this moment, but let us not go into that. We are going to discuss the spectroscopy part of it, mostly the how the nuclear spins states are looks like, what are the transitions are going to be, whatever sir has discussed. So so what I am going to do, I will write those, but I'll be taking your help to solve that. Okay.
Sure,
So
sure.
mostly you are going to do that. So let us first start with. Uh, anyway, you have heard of the 2ni plus 1, those kind of rule, right? So some
Yes,
coupling things. So basically we are going to arrive at that formula. That formula is used in a day-to-day basis for a organic chemist or inorganic chemist, even we use that without even thinking what is actually happening. Actually, we cannot really think of that at every point of time, but at least for once we should know that why that splitting is happening. If the splitting is not happening, why it's not happening. At least for once we should have that idea. Later again we are going to use the general nomenclature we or general thing what we do, that 2ni plus 1, suppose a proton is there, suppose ch, so the most common is what have been taught in the class is ethanol, right? ch3 ch2oh. So
Yes.
there some one of the proton is going to be it going to have a quadrate, and another is going to be I think triplet kind of, right? So it is something like ax. Those kind of system we are going to discuss, but uh, here we are going to see the quantum mechanical aspect of that. Let us start. So let me go to the pain mode. So let us first start with a system. What happened? Okay, I think it's not connected. So for the connect. Give me 1 minute. Now it yes. So we will start with the basic system, but not exactly basic. Acha, let me at least write few of the things that your interaction energy is going to be minus mu
B.
into what?
B.
B, right? The applied uh, uh, magnetic field. And
Yes.
mostly we are going to discuss this magnetic field is applied to the Z direction for our uh, uh, um, for our these cases. And this mu is here is you can write it in terms of the uh, gamma. Sorry about that. The gyromagnetic ratio multiplied by your uh, nuclear moment, right? Nuclear orbit.
Um,
So yes, now you can have. So what can be the what is the nuclear quantum number? What do you think for a proton kind of a proton? Okay, so
it's half.
what is half? And then if it is half, so I is half, right?
Yes.
So
Mm.
what are the I is half? Then what is the length of that orbital angular momentum vector?
It is root over of I into I plus 1 h bar. Yes.
Yes, similar to the orbital angular momentum what we have learned. This right now I'm going to say
Yes.
I magnitude, right?
Yes.
So this is H card. What about IZ?
This
That is
is M h bar.
yes,
I
or MIH or M you can say, right? What is this MI gives us the idea about? This gives us the idea that what is the Z component of it, right?
Yes.
So
Yes.
suppose for a proton kind of a system, what do you think? What is the uh, what are the
It
two possibilities are there? Alpha and beta, plus half and minus
and
half.
1 plus 1. Yes.
Yes. So and from here, actually, what you are going to see is that your we are actually going to deal with as I told you that we are going to talk about the magnetic field is going to operate along the z axis. So we are going to think about that only. Okay. and and also you have learned about the chemical shift in the first uh, class of the first class means the first class of the NMR spectroscopy, right? So we are going to the system AX kind of a system. What do you think AX system means?
Means they have there is a large variation in their this magnetic moment.
Not actually. Not large variation. This actually means that they are chemically shifted. They are not actually in a same environment. So, so suppose CH3, CH2, OH. Okay, this is for ethanol. So
Yes.
suppose you can still say that these protons, right? These
Yes.
protons, if you think about all the three protons on a same carbon, then
Yes.
they are called equivalent protons. So
Yes.
they are kind of A3 kind of a case. Okay.
Okay.
And this proton, which is a different proton, having a different electronic environment around this, actually is going to have the different shielding constant due to that, and due to that they are going to experience different magnetic field due to that shielding constant, as you know, and due to
Yes.
that its chemical shift is different than this, and that difference is significant, and
Yes.
that's why it is called AX kind of a system.
Actually, this ultimately results into the change in their magnetic moment. Means effective magnetic moment.
Effective magnetic moment, yes, that's true. But in a crude sense, when you start
Yes. Yes.
AX
Yes.
kind of a system, then if one asks you what is a AX kind of a system, then it is better to say that we are dealing with two uh, new NMR active NMR active nuclei which are chemically shifted.
Yes.
Okay, and when we are going to discuss A2 kind of a system, we are going to discuss it today also. So that means we are dealing with a equivalent. They are not separated that much in space. Okay, so
Yes.
so what could be the possibilities? So one could be both are alpha, right? Alpha A, alpha X, right? One of the state. Another state could be what? Can you tell me?
Beta A, beta X,
Beta A, beta X, and another.
1 by root 2. No, no, yes, alpha A, beta X, beta A, alpha X plus.
Yes. See, when that, sorry about that, when that your 1 by root 2 came, that came during the your
Normalization process.
A2 kind of a system, because in that case we could not specifically differentiate two nuclei. Here we can differentiate. We know this is A and this is X.
Yes.
When both are A kind of, then you can't distinguish between them. So that's why you need to take a linear combination. But here you can distinguish. Then alpha, sorry, maybe I will write beta A, alpha A. So let me give you another condition where your shielding constant is lesser than the shielding constant for X. So what that is going to result into? Main, first of all, you think shielding constant is less for A than X. So that means A is going to experience more of the applied magnetic field than X.
Yes. Yes.
Then
Yes.
what is going to be the uh, 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 what the energy gap, or where the energy gap is going to be more
In the
between
case of
the,
A, it will be more.
it will be more,
And in, yes.
right? So if you think of the chemical shift, then A is going to be more chemically shifted, right? It
Yes.
is called downfield. So this nuclei is going to be downfield, and so in that prospect, if you think your alpha A, alpha X going to be here, and you can understand the beta A and beta X are going to have the highest energy, or they are going to destabilize. So so what do you think in presence of, what will happen in absence of magnetic field?
Uh, In
So the,
absence of
in absence of magnetic field.
magnetic field, I think it's like this beta X will be lower. The energy will be lower, and alpha X, alpha A will be higher energy compared to in the presence of when the magnetic field is present, because it
No,
is. Yes, I think
says
so.
actually these all the states actually are degenerate when the
Yes.
magnetic field is not there. Now, when the magnetic field is given, and depending on the how strong magnetic field we are going to provide, then only they are going to split.
Yes.
So when
Here
they
is no split is there. Already they are splitted. So in this case, only
no
the
no
alpha X.
no that is not what I discussed. I was asking. I was asking that suppose there is no magnetic field yet. So then what will happen? Then they are all are degenerate. Now a magnetic field, suppose this B0 is given, then only they are going to separate it into the four state. And then we are going to involve the coupling. So we are not talking about the perturbation or coupling yet. We are just discussing the unperturbed system. That is, suppose here there is no coupling. Maybe that is a that is something ideal case, but that is not usually happens. But right now we are going to discuss that first, the unperturbed system, and then we'll go to perturbation. But before that, suppose there is no magnetic field,
Then
then
all the energy
all
in
are
a
degenerate. Yes, all are
single line will
degenerate.
be. Yes,
And
yes.
not even single line. There is no transition. If there is no
Yes, no
magnetic field,
transition.
then
Yes,
there is
yes.
no transition. Now, when we have applied a magnetic field, and depending on how strong the magnetic field we are going to provide, depending on that, the splitting will be that much more. It is not like the rotational spectroscopy or vibrational spectroscopy where there was some definite or quantized values of uh, your quantized value. So those values are constant, right? And we are trying to get a resonance condition or something like that to get a transition. But here, the we are what we can actually play around with the magnetic field to get a better splitting or lesser splitting. You get it? That how much the splitting will be there, that we can decide on how strong magnetic field we are going to provide.
Yes,
And alpha A beta X and beta A alpha X are going to be somewhere here,
yes,
okay?
yes. Yes.
But they may not have the same energy yet. And we are going to discuss that which one has the higher energy or more. And what is your Hamiltonian for that? So unperturbed Hamiltonian, and that is written in terms of gamma, your gyromagnetic ratio, then your B0 applied magnetic field, and then your, so this is your sigma A in case of your IZ, as we already discussed that we are going to discussing that magnetic field is applied along the Z axis, IZ and of A, okay, and then plus 1 minus sigma X IZ B.
Yes.
So IZ of B, sorry, IZ of X. So I often I am going to make this mistake often. Please pardon me and remind me wherever I am doing that B thing. So why did I write it like that? So so right now in a this is in inside a molecule. So there are separate electronic field, electronic environment around the A and X nuclei. So we have already discussed that shielding constant for A is lesser than shielding constant of X. So this is going to be the Hamiltonian. Okay. So your A and X, they are going to have different splitting. If they would have, they are in a bare atom, not in a molecule, right?
Yes.
So how do we get the energy of a particular state? The energy or the average value that actually can be decided like this: psi, your Hamiltonian operator, and psi, right? So maybe for here, for unperturbed energy, we can write E naught, right? Oh, sorry, this should not be called E naught or E zero. It should be called first order. Sorry, zeroth order. Zeroth. Okay, that is the actual thing, what scientific thing to say, not the psi naught or H naught. H zero. That means the zeroth order. So there is no perturbation. Okay. So this is the actually, I think, one of the quantum mechanical postulate where you using this. So and obvious psi is normalized. If it is not normalized, then if it is not normalized, then you would have to use this,
Yes.
right?
Yes.
But we'll assume that for our case they are normalized. So I'm not writing it. Huh? So
Yes.
we are going to get the energy for each of the state and decide that where they are going, where they are, and which transitions are possible. Okay. So let us do that. So the first state is alpha A, alpha X. Okay. So the energy of that, let me write E1. Okay. Zeroth. So that would be alpha A, alpha X. So this is your state. Then your Hamiltonian is given minus gamma B naught. Then what was there? Then there is a third bracket 1 minus sigma A Iz operator. So I should write operator everywhere. So these are actually operators, right? I
Yes.
should. So Iz A plus 1 minus sigma X I Z X. In between, if you have any question, please
Sure.
ask.
Sure. Sure.
So see, now we can take these actually out of the integration, right?
Yes.
And this is the your states. So how do we proceed? That we are going to operate this
On
uh,
Z.
nuclear momentum operator on this, right?
Yes. Yes.
And so let me take gamma B0 outside. Then alpha A, alpha X, 1 minus sigma A. I could have take this thing out also. And it is going to operate on alpha A, alpha X. Let me end one of the bracket. And then suppose I have another alpha A, alpha X, 1 minus sigma X. It is also going to operate on alpha A, alpha X, right? And third bracket. Now see, we can even take this out. 1 minus sigma, this is constant, right?
Yes.
Sigma A, alpha X. Now you tell me the IZA operator that is going to operate on only the A atom, not the X, right?
Yes. Yes. Yes.
Let me write alpha X here. And what does it is going to generate alpha Z A when it operates on alpha? So it is going to give you the Z component, right?
Yes.
And that
Yes.
for alpha, what is the Z component? That is H cut by 2,
MZ. Yes.
half into H cut, right? And it is
Yes.
going to be give me this back. Okay. So
Yes.
similarly, I will write this also. And IZ is going to operate on alpha X only. So
Yes.
I can write it first there. And same thing. H
Yes.
cut by 2 alpha X.
Okay.
So you can see gamma B0, and this is a common thing that is coming out. And if that comes out, your in bracket alpha A into alpha X, alpha A into alpha X. So that
yes,
is your normalized condition, and that is going to give you, as it is normalized, so it is going to give you 1.
yes,
So 1 minus sigma A plus 1 minus sigma X, that is going to left, and that is actually what? Minus gamma B0 H cut. I can write it 1 minus sigma A plus sigma X by 2, right?
yes, yes.
So I can write it like that. So you see that when there was no, so there is no, so suppose B0 is 0, means there is no applied magnetic field. So you can see that the energy was 0, right?
Yes, yes,
From this formula. So now when there is a B0, so see now your energy is negative. That means it is being stabilized.
yes,
So so when all the states were, suppose it was 0 here, somewhere here, then it becomes stabilized. And let me use another color. Maybe I will write it here. This was alpha A, alpha X, and energy of that state came out to be minus gamma B0 H cut 1 minus sigma A, sorry about that, sigma X divided by 2, right?
yes.
Now similarly, if we do it for beta A, beta X, what is going to change?
Only the minus side will become plus. This gamma V0 is cross
and
1
that
minus.
is and that is because IZA is going to operate on beta A, IZX is going to operate on beta
Yes,
X, and that is your that is eigenvalue equation, and that leads to minus, right? Mi
yes,
is minus for beta, right?
yes, yes,
So for that I'm not doing it, but you can see that energy is going to be plus gamma B0, because minus sign would be there only, and rest will be same, right?
yes,
X by 2. So you can see here there is no stabilization. So so when the B0 is given, then it is going to destabilize, right? So
yes.
the energy would be,
Undetected.
so energy would be something here. So that is beta A, beta X. So I have given you, so as you already know, so it feels like a spoiler that the two that is going to be
Maximum
there.
energy.
Yes,
Sir also did this yeah, in the class.
yes. So I think in the first lecture he gave you a idea where, so generalized thing, where he has not dealt with the shielding constant, and then on the second lecture onwards he introduced the shielding constant, and then everything fall into the places.
Yes,
So now what are the two states that are left? One is alpha A, alpha X, and another is beta A. Oh, sorry, beta A, alpha X, and alpha.
yes.
Do you think both the energy are going to be same or differ?
They are different depending upon the setting.
Okay, let us check. So you this is alpha A, beta X, then your, so I can take your minus gamma B0 outside, right?
Yes,
And 1 minus sigma A Iz operating on A plus 1 minus sigma x alpha A beta x, right?
Yes.
So here what will happen? Minus gamma B0 is outside, alpha A beta x, then I that is going to operate on alpha A only, beta x will stay as it is. Then we can close it and plus alpha A beta x, then 1 minus sigma x Iz x will operate on beta x and alpha A
Yes.
will be something constant, right? So from the first integration or first uh, thing, so 1 minus sigma A is going to be here, and then alpha A beta x, and then Iz A is going to operate on alpha A, and that is going to lead to your h
Yes.
cut by 2 alpha A,
Yes.
and beta x will remain as it is.
Yes.
Then here 1 minus sigma x I can take outside,
Yes.
and alpha A beta x.
Minus h equals by 2.
Yes, here it is going to minus h cut by 2, and it is going to lead to the same eigenvalue, eigen function, and like this.
Yes.
So I can B0, I can take h cut by 2 outside, and then again, if I take them outside, so this has become the normalized conditions, so they are going to yield me 1. So 1 minus sigma A I am going to get from here, but from here I am going to get 1 minus 1 minus sigma x, right?
Yes.
So how it will look like? Minus gamma B0 h cut by 2.
Sigma x minus sigma.
So 0. 1 minus 1 is going to yield me 0. So let me erase that. 1 minus 1, it is going to be sigma x minus sigma a.
Minus sigma.
Sigma x minus sigma a, right?
Yes.
Then for this, so, and what we learned, that sigma a is less than sigma x,
Yes.
right?
Yes.
So what about this part? Sigma x minus sigma is a positive quantity.
Yes. Positive quantity.
So you can see that your alpha a beta x is also going to be stabilized,
Okay.
right? Now let
Yes.
us check for this.
It will just flip the sign.
Yes, so we will do it once.
Yes.
Alpha beta a,
Okay.
alpha x, 1 minus sigma a, Iz a, 1 minus sigma x, I x. Do not forget to give the cap sign because they are operators.
Yes. Yes.
So maybe we can jump a few steps. Maybe we can directly write the third part. Gamma B0, 1 minus sigma A, beta A alpha X, right? IZA is going to be operate only on the X, right?
Yes.
Only of the X. Sorry, IZA
On
is only going to operate on
on fire.
beta X. So in the first, you are going to get H cut by 2.
No.
Did I? Acha, I have made a mistake here. Sorry about that. I
Yes.
have made a
Zero.
mistake here only. It is beta A alpha X.
Yes.
So IGA is going to operate on beta A. So that means I am going to get a beta A
alpha
with
x
this
minus h bar minus h bar weight.
right. And then I am going to have 1 minus sigma x beta A alpha x, and IGX is going to operate on alpha x. So that is going to remain plus h cut by 2 beta A alpha x. Okay. So I will write it like the previous case. I will take h cut by 2 outside. So I will be left with minus 1 minus sigma A plus 1 minus sigma x. So if I have to write it like the previous case, h cut by 2, but here what it is going to be? A
Sigma
sigma
m
A minus sigma x.
minus
And
sigma it is
definitely it is negative, so this is a positive. Overall, this is a positive quantity, right? And what
yes
about these previous two? Previous two cases, you can see sigma A plus sigma x. So that doesn't
yes
mean anything. So,
yes
and these values are very, very less than 1, right?
yes
So these
yes
values are very, very less than 1, and that is why overall you are going to get a positive value from here, and that's why it is negative, and this value is positive, right? So
yes
what we learn from here, that from the energies, that there are two more states. So this is not to the scale, obviously. So your this is your beta A alpha x, and this is your alpha A
yes
beta x, and this is your third state, and that corresponds to minus gamma b0 h cut, right? And then by divided by 2 also, right? And sigma A minus sigma x.
yes
And this is, sorry, minus gamma b0 h cut by 2 sigma x minus sigma x.
sigma
That is why, so suppose this was your 0. So here your all four were degenerate when no b0. Then in presence of b0, it has splitted into these four from here. And how much did they split? So if this is the zeroth line, then these are the energies. They have stabilized or destabilized, right?
yes
Negative means stabilized and positive means destabilized. So now tell me that what are the here your spin flipping should be there for NMR activity, right? So your
yes
alpha, and one thing is that one transition, a transition is possible, one transition is possible by one photon. So,
yes
okay. And
yes
what we actually do, we create the magnetic field, sorry, we apply the magnetic field to split them.
yes
Okay. And now we use radio frequency, and at that particular resonance frequency, which is also known as Larmor frequency, their precisional frequency, they are going to resonate. And at that particular resonance frequency, we are going to get some observance or some spectra there.
yes
So that is the operation what we do. That when there is no field, all of them are degenerate. Now we apply some field. The spin state, nuclear spin state, they actually now become non-degenerate. They split into different energy levels, and now according to the selection rule, there is going to be some transitions, and those transitions can be monitored by uh, giving a radio frequency to this, and the resonance radio frequency are going to be absorbed, and that's how we are going to get some spectra. We will get some transmittance, and that can be converted into absorbance, right? And some peaks are going to come that this energy has been
Abs-
uh, yes,
abs-
right. So now tell me, what transition can be possible here?
This alpha A alpha x to alpha A beta x is possible, or alpha A alpha x to beta A alpha x is possible.
So
Only
this
one
is
spin flip is possible.
so this is possible.
Yes.
Alpha A to this
Beta x to yes.
is this possible? Alpha A
Yes.
alpha X to alpha A alpha. Okay.
Yes. This is also possible.
Is it possible alpha A alpha X to beta A beta
No,
X?
no, no. For
Why
a single
not?
photon, for a
Right.
single photon, two spin flip are not possible.
Okay. What about beta A alpha X to beta A beta X? Is this possible? This one?
Yes, it is possible.
What about alpha A beta X to beta A alpha X? Is this possible? These two from here
No,
to here? No.
no.
Right? Because again there are two spin flipping. So
Yes.
here, what is the flipping? Here we are flipping the X only, right?
Yes.
Alpha X to beta
Beta.
X. Here we are dealing with alpha A to beta
Beta.
A. What about here?
That is
Uh,
alpha x to beta x.
alpha X to beta
Beta.
X. And another one is possible alpha A beta X to there.
Yes. Hmm.
So here alpha A
To beta.
to beta A. Now if you think about the energy difference between E4 and E3, can we do that? So if we do that, let me use another color, colorful things we will like. If we take a minus between these, let me take this thing as common. Okay, so we are going to get 2 minus sigma A minus sigma X, right?
Yes.
And then there is some minus minus plus, so it will become plus. So gamma B0 H cut by 2 is there. We have sigma A minus sigma X, right?
Yes.
So what do we actually have? Gamma B0 H cut by 2
Into 2 minus.
sigma A cut
Yes.
and 2 minus 2
2 sigma x.
2
Sigma
sigma
x.
A. So we can take this 2 outside and 2 will cut. So
Yes.
let us erase this 2. I'll write 1 here. So what do you think? What is this quantity?
Is normal frequency.
So this is the energy.
Yes.
So your this is one delta E. So this
Yes.
is for X, right? This can be, you can write it in terms of H into nu X, right?
Yes.
So are you getting it? What I'm trying to say? So the
Yes.
Larmor frequency, this is going to be equivalent to this,
Yes.
right?
Yes.
And what about, so this is what we talk, right? E40 minus E30. That you can see that spin flipping is of X only. So
Yes.
that's how we know. What about so we know that E30, E20, we will not do that because we know we are not going to get anything from here. What
Yes.
about E30 minus E20? What we are going to get? Let me write E B
It is
gamma
not
with
possible.
3 minus 2 is not possible. Sorry, 1. So let me write it like that. So then we are going to get uh, um, minus minus plus, but we are taking, suppose we are taking a plus common, then minus plus, and then we are minus minus plus 2 minus minus. So here, from here, you are going to get gamma B0 H cut sigma x, they will cut 2 minus 2 sigma A, and that 2 will cut, you are going to get 1 minus sigma A, right? And that
Yes.
is actually your H nu A, right? So
Yes.
similarly, you can say that E zeroth 2 minus E zeroth 1, that is going to lead you to H nu x. And again, your, what is the another transition we can discuss? E3, E4, E no E zeroth 4 minus E zeroth second. So that is also going to be your H nu A, right?
Yes.
So you can see there are four transition is possible,
Yes.
but each so four transition are possible, but two are of them of the same energy. So we expect two of them to be same intensity. And why same intensity? Because again, intensity is depending on the population, but as we already discussed, this nuclear spin, these states have the energy very very less. So at room temperature, these states, all these states are populated, right?
Yes. Yes.
So you are going to expect a plot in chemical shift, maybe delta, where delta is increasing in this side and this is intensity, or even maybe let me write energy for now, or nu, right? So nu will increase on this side. So what do you think? Which has the higher energy between that? Sigma A is smaller than sigma x, right?
Yes.
So H nu A is going to be
Higher
la-
than I think. Yes.
so this side should be A, right?
Yes.
If nu is going that side. So for A you are going to see here, and X you are going to see here. In case of nu, but when we will say in terms of delta chemical shift, are we saying the correct thing? Uh,
Yes. No, I think.
Let me check once. Actually, we are saying the same correct thing, but actually I have as we have taken the energy to be increasing this side nu, that's why
Yes.
it is same. So your delta will also increase, but let me maintain the same convention. Let us say the energy is going to increase this side. So the same thing, just we have using the old convention. So your nu A is going coming here and nu X is going to come here. And
Yes.
what is chemical shift? Chemical shift is your, if we can write maybe here. Can you tell me what is the chemical shift?
That's it.
1 minus uh, so B, those things are going to cut. Uh, Gamma is going to cut. Um, Sigma A minus, um, let us actually check the notes, right?
Yes.
Let me go to the This is what your Larmor frequency is, chemical shift, right? So this is the Larmor frequency you're going to get, and this is in delta scale. 1 minus sigma into B0, B0 is going to get cancelled, minus 1 minus sigma 0. What is sigma 0? Sigma 0 is the for a reference, right?
Yes.
And
Yes.
what do we use as a reference? We use TMS, trimethylsilane. So let me give you a basic idea why. So we do not add TMS in our solution. The TMS is already there in this deuterated solvent. Okay.
Okay.
So and why do we use a deuterated solvent? What do you think in
Because
NMS?
it will not interfere. That's why it is two. That's why it will
Yes,
not.
yes, it is not. But what do you think? The deuterium, does it have any nuclear spin or not?
No, I don't think so.
It has. It is actually has a integer one, I guess.
Okay.
Yes, the proton is half, but you are looking at, but you are going to look at proton NMR. So how can you
Yes.
see the deuterated? Actually, we use deuterium solvent for two reasons. One thing is that with using the deuterated spectra, if you use a proton NMR kind of a thing, then your peak doesn't interfere. Obviously, solvent doesn't interfere. And another thing is that shimming and some kind of shimming thing is there of the magnets. So that is actually a coiling and shimming, something like that. So for that reason, you want a deuterated solvent. You may look into that, but this is what is a chemical shift, right? So you can. So this is what we were saying. 1 minus sigma minus 1 minus sigma 0 by 1 minus sigma 0. So I can write it for our purpose here, that 1 minus sigma A, suppose 1 minus sigma 0 divided by 1 minus sigma 0. So actually this chemical shift doesn't have the uh, as such, they are independent of the magnetic field, right? But that splitting needs the magnetic field. Okay, don't get confused between both the things. Okay. Now, this is how your spectra is there when there is no perturbation in case of AX kind of a system. When the perturbation comes, right? Now, what is going to be your perturbed energy? So, let me write coupling in AX system. So now the coupling in AX system is something like you are going to use Hamiltonian. So your total energy or total Hamiltonian is going to be your zeroth plus this perturbed one. First order perturbation we will think of. We are not going into the higher order perturbation. We are only discussing about this. And that's why your energy, total energy is going to be your zeroth order energy plus perturbed
E1.
energy, E1. And again, not E1, E first order.
Yes, first one.
So, so this also you can get it from here. Sorry, my bad. Using this. This we are directly using the perturbation theory and we are thinking of like this. Okay.
Yeah.
And your H1 again, sorry, the Hamiltonian first order is uh, H JAX, then your H cut square, and there is a vector. And as this is a vector, you need to consider and dot product, right? So I x small x, then I A Y I X capital Y small capital X small y, then I Z sorry I A Z I X capital small z. Why are we taking all of them? Because when we are talking about coupling, it's not like that you can talk, the crosstalk is only there through a certain direction. The bar magnets, if you think of them as a magnet, they can couple through any of the things. But your main applied magnetic field was along the z direction, right? So when this perturbation actually is there, the coupling, we are thinking of the we are actually treating this as a perturbation. So they are going to interfere with the e- energies of the electronic nuclear states, right? So the states are same, alpha A, sorry, alpha A, alpha X, then your alpha A, beta X, second state. As you already know the energy order, so that's why I'm writing it like that. Beta A, alpha X, and beta A, alpha, beta X, right? These four.
Yeah.
Now we already know the zeroth order thing. Now let us find out that what is going to be the first order energy correction to the alpha 1. Individually, we have to do alpha A, alpha X, H, H cut square, JX that we can take outside from the next time onwards, right?
Yeah.
And there we have, actually, let us take this outside. Then IAX, IX, X operating on maybe I will do a step jump. I hope
Yes, yes.
that won't be a problem. Maybe I can take a bracket here, alpha A, alpha X, then Y, IXY, then alpha A, alpha X, right? Then we have alpha A, alpha X, IZ, IAZ, IAX, sorry, XZ operating on alpha A, alpha X. Okay,
Yeah.
and we can close the third bracket. See, now we are in need of a different functions. Actually, I will write it here. So let me actually write another step. For the first one, we are in need of this is going to operate on alpha A and this is going to operate on alpha X, right?
Yes.
Then alpha A, alpha X, this is going to operate on alpha A
Yeah.
and this is going to operate on alpha X. Then This is going to operate on alpha A. Okay. Now we are going to need this eigen, these four we don't know. So let us write them once. So I will write it here, here maybe, that Ix when it operate on alpha, it gives actually beta, not
Yes.
pure alpha. Then when Ix operate on beta, it gives h cut by 2 alpha. Similarly, when Iy operates on alpha, it gives back beta, but IH cut by 2.
Yes.
And again, when Iy operate on beta, it gives minus IH cut by 2 alpha. And the others we know, right? IV, how does it operate? So I'm not writing them.
Yes.
So let us come back here. So we got H by H cut square Jx, right? Then alpha A, alpha X. So we are going to get alpha A. So X is operating on alpha. So we are going to get H cut by 2 beta A, right?
Yes.
And the next one, what are
This
we going to get?
this is h cut by 2
H cut by
beta
2
x beta x.
beta X. And then here, alpha A, alpha X. IY is operating on alpha.
Yes.
So IH cut by 2
By
beta
yes.
beta A, right?
Yes. Yes.
What about the next? Alpha Y is operating on alpha Y is operating
Minus
on alpha X. So again IH cut by
minus
2
yes.
alpha X,
Yes.
right?
Hmm.
Uh, then we have
Then
alpha A, alpha X, and this is
h cut
easy. H cut by
square by
2 alpha
yes.
A, H
Yes.
cut by 2 alpha X, right?
Yes.
Okay. Now you
Only
see
the last
one thing.
yes.
Yes, tell me.
Only the last thing will survive. Rest of
Yes,
the
this is going to be zero, right? Because not a normalized condition for these two, right? Orthogonal
orthogonal.
condition. And only this is going to survive with some value. So that we are going to write. So that we have that first order correction to that h over h cut square jax. Okay.
Yes.
Then we have, okay, we will not write the this because we know that is going to be 1. We are going to get h cut square by 4, right?
Yes.
And h cut square is going to cut from the numerator and the denominator. Ultimately, you are left with h jax by 4. So this is the perturbation you are going to see for the first case, first
Yes.
state or the lowest state. So you are going to see. So all the things are positive.
Yes.
So you are going to see a destabilization for the first state. Okay.
Yes.
So
Yes.
maybe I'll write it here. So first all the things are degenerate, then it becomes like this. This is your beta A, beta X. This is your beta A, alpha X. This is your alpha A, beta X. Then this is your alpha A, alpha x, right? Now there is a perturbation, and you saw that there is a destabilization.
Yes.
So that destabilization is by AJAX by 4. So what do you think when what is going to happen for beta A, beta X?
It will shift.
So first two are going to be 0, right?
Yes.
Because
Yes.
beta A, beta X, and this side it will be alpha A, alpha X.
Yes.
Only this part is going to change.
Yes.
So beta A, beta X, and same thing we will get. So minus H cut by 2, minus H cut by 2. That is the
You
only
get
difference. But minus
it.
minus will become plus.
Yes.
So
That is also destabilized
yes,
by
that
the
is
same
also destabilized for the
by the same amount.
yes. So H J X by 4. So we can draw it here also, right?
Yes.
Beta A, beta X, alpha A, alpha X. What about these two? That would be interesting to see. So have you done it in so while writing in your notebook or while reading?
Yes. During the class,
Yeah,
I also thought with sir.
it was very necessary. Else
Yes.
you will lose track of this. Yes.
Yes.
Now let us do for the second step, that was alpha x beta x, sorry, alpha a beta x, and your h j x by h cut square is there. So actually we can do a step jump here.
Yes.
Alpha x is operating on alpha a. This is going to operate on beta x, right?
Yes.
And then alpha a beta x I a y is going to operate on alpha a I x y is going to operate on
Beta. Beta X.
beta x, then alpha a beta x I z, sorry, I a z is going to operate on alpha a, and I x z are going to operate on beta x. Now there is going to be some change. Now you see alpha a beta x, that will lead you to alpha a x operating on alpha a. What to alpha a x? Sorry, means alpha x is operating on alpha a. So that is going to lead you to h cut by 2 beta a.
Beta X. Yes.
And here it will going to lead you to alpha x, right? With
H cut.
h
H
cut
cut.
by 2. And similarly, alpha A, beta X. Alpha A operating on this IH cut by 2 beta A,
Yes.
and this actually due to minus
And
IH cut by 2
right.
alpha X, right?
Yes.
And then alpha A, beta X. IA, IZ operating on this, again this came to our 4
Minus h cut square by 4. 1 minus n.
here.
Yes.
Now it is
No,
not as simple as
no.
okay.
This IAZ operate on alpha, it will produce alpha, na? Not beta.
Sorry,
This
sorry,
last,
sorry. True, 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 true. Where is my cursor? They are eigenvalue equations. Now let's see what we have here. H cut square by 4. We have alpha A, beta X. We have
beta alpha s. That is again become 0.
that will again become 0. What about this part?
Same 0. It will become 0.
So let us write. So let me write 0 for all of this.
Only the last integral will survive, and it is minus h cut square by 4. Yes.
So minus h cut square by
4.
4, and then it
That
is going to survive. So this is minus h jx by 4. What do you think it is going to be similarly the third state, like the beta A, alpha
yes.
x? The first two terms are again going to be 0.
Yes. Yes.
Beta A,
Same.
alpha x.
That is again stabilized by the same amount.
Yes. So here you can see. So you need to. So this was your E04. This was your E03. This was your E02, 1. And now this is your the final energy is your
That is in E11, not 0.
what?
Okay, na, fine. That is 0th order. Okay,
Yes,
fine.
yes. And then it is your zeroth order plus your perturbation, what we just got, right?
Yes.
So similarly here also you can, if you see, there is going to be 4 transitions, right?
Yes.
Mm, here to here will lead to alpha x to beta x. Here to there, alpha a to beta a. Here to there is alpha x to beta x,
Yes.
and
2 to 4.
this was alpha a to beta a, right?
Yes. Yes.
So overall you can see, but previously you saw the energy levels are same. But
Yes.
now suppose this is your E4, this is your E3, this one. This is your E2, this is your E1. So your E4 is, so E4 minus E3 Earlier, how much did we get? We got uh, H new x, right? And now
Mm.
we extra have HJAX by 4 for the upper energy and minus minus plus for the.
Yes.
So actually H new x plus
Yes.
H
H
Jx
J.
x by 2, right?
Yes.
Again, if you see for E4 minus E2, earlier it was H nu A. Now the upper energy has by this and this has done similarly, right?
Yes.
Similarly for how much was it?
Minus H J by 2.
No,
H new. Yes. This first term will be there. Minus H J by 2.
and then it was minus and this plus, so it would be minus, right? You got my idea. So it
Yes.
it has decreased the upper
Yes.
one, and
Yes.
this one has increased. So it was plus, but it is there in minus. Plus would be minus.
Yes.
So
H new A minus H J x by 2.
right, sorry. And then E2 minus E1. Similarly for same will be happen for this, right?
Yes.
So you can
But
see that earlier what we got, if this is new, so this was for A and this was for X, right?
yes.
But as you can see, now we are going to get four transitions. Earlier also we got four transitions, but at two energies. But now the energies are different for the transitions, right?
Yes.
So X can have two type of transitions, one with the energy plus Hj Ax by 2, another with minus Hjx by 2.
Yes.
So the reformed one would be here,
Yes.
one plus and one
Yes.
minus energy,
Yes.
and I can show you that. Oh, maybe I can use a different color. Instead of the single line, now you are getting doublet. Okay.
Yes.
What will happen if it is a AX2 kind of a system?
AX2
Yes. Then,
is.
then what is going to the effect on A because of X? 2X. There are 2X.
Yes.
Think of it like that. It is going to simultaneously split the lines of A, right?
Yes.
So then for a AX2 kind of a system, So this A line is again going to split.
Yes. Using
Similarly, using the same thing.
yes, yes. Every line will be splitted. Means A.
Yes. And half will come from here and half will be there from this splitting. Right?
Yes. Yes.
But will X split or not? For that we need to discuss A2 kind of a system, right?
Yes. Yes.
So, but I don't think we have that much time for a A2 kind of a system to show you.
Yes.
But what is going to happen? Can we guess?
Resonance kind of thing. Yeah.
Uh, a resonance kind of thing is happening everywhere. So you need a resonance to get the. So that is why it is NMR, nuclear magnetic resonance.
But
But
in X also the intensity will be higher. Means 2x will superimpose on each other and it will create a higher intensity.
yes, so means the splitting will be there.
Ye-
But what you are going to see due to that, the splitting is going to be different than what we are getting this splitting here. And the only reason is in case of A2 kind of a system, your uh, shielding constants become same. Here your shielding constants are different, right? Because your electronic environment is same, different. Now when you are discussing A2 kind of a system, that means you are discussing equivalent kind of a nuclei. They are on the same atom or they're attached to the same atom, something like that. So now you can think that uh, what will happen. So now you cannot distinguish. So even though the shielding constants are same, but now you can't distinguish the you can't distinguish the nuclei. What you are doing it for A and X kind of a system, and for that your let me save it. So first, let us think how the splitting. So first there is all these are degenerate.
Yes.
Then some splitting would be there, and those splitting are going to be something like that. I'm not showing you here. So it is alpha alpha, but let us write 1 and 2.
Yes.
Okay, there will be beta 1 and beta 2, right? And the Hamiltonian is actually a little different, not different to be honest. Just see 1 minus sigma 1 on
I
Ig1, then 1 minus sigma. Actually, I can write sigma only, not sigma 1, because both the values are going to be the same. Okay, and now you cannot distinguish between them. So that's why you are going to write alpha 1 beta 2.
minus
Another
plus
possibility is beta 1 alpha 2 and plus minus a linear combination. And for normalization condition, you are taking this 1 by root 2, which was not required earlier.
yes.
And you can calculate the energies, and you will see the energy for these two are actually zero. So that's why I have kept in this line. For them, the energy they are still at that zero because for alpha it may increase, for beta it will decrease. So they will take care of each other. You
Yes.
got my point?
Yes. Yes.
So alpha 1 beta 2, for 1 it will increase and for beta 1 alpha 2 it will decrease. So
Yes.
that's how it will get cancelled. But So now when there is no coupling here, you can see how many transition can be possible. Alpha 1 to alpha 2, this is possible.
Yes.
To right? Only one splint flipping.
Yes.
This is also possible, alpha 2 to alpha 1.
Yes.
This is not possible, and this is again possible.
Yes. Only two.
But all of them are going to come at the same
Yes.
energy,
Energy.
right? So you are
Yes.
going to see only one. Now, when your coupling will come, now it will be interesting. Earlier, it was something like alpha 1, beta 2, a alpha A, beta X, or beta A, alpha X. Now it is a little bit bigger, right? Now you have to, that is going to be a little bigger integration you have to solve, but you will see that three of the cases it will increase, and one of the cases it is going to stabilize. Okay, for alpha 1, alpha 2, and beta 1, beta 2, it is the same thing.
Yes.
So let me write coupling in green. So what will happen? So this will again increase by,
Yes. H cut
yes, h j x by
by
4.
four. Yes.
This
This
will
is
also
again.
increase
Yes.
due to time constant. I am just showing you, and one of them
Will be
will also
uplifted and
increase,
yes.
destabilize,
Yes.
and one of them is going to destabilize three times of that.
Yes.
Now you, when you see the transitions, so now you work out these energies and these energies, and then you are going to see actually there the splitting is there, but
Okay.
the difference is again the same.
Okay.
Maybe uh, we can go to Datta's lectures, last one. So this is what we are discussing. Can you see my screen? I
Yes.
think
Yes.
it's a little visibility a little less. So so the perturbed A2
Yes.
system. See,
Yes.
so
Yes.
the minus one is going below. Rest of them are getting enhanced. Now where is the, no, he has gone a little far. Now from here let us try to see. So see, only two transitions will be possible then. Okay, that alpha 1, alpha 2 to the third state,
Yes.
and due to delta S is equal to 0, that is your um, the tot- total change in the spin should be 0, like
Yes.
what we used earlier also, right?
Mhm.
So that's why you are going to even see the two transition and the energy difference are same because they are lifted by the same energies,
Okay.
and that's why even though there is some splitting, you are going to see no change in the spectrum. So there is
Yes.
splitting, but that is not visible. So
Yes.
with that, we can actually go to the assignment solution. So actually, question number 8 on the assignment have that question. In formaldehyde, the structure is it is a aldehyde. Two protons are there. Okay. So this is the
Yes.
structure. So only one proton NMR line is observed.
Yes.
The options are two chemically equivalent protons do not couple with each other, two
They will
chemical
couple with
each other,
they
but it does not show up in the spectrum. Okay,
Spectra, yes.
that is actually the scientific answer. Most of
Yes.
the time, you will hear that equivalent proton doesn't couple. They actually
Yes.
couple.
Yes.
Why?
Yes.
Why don't they are going to couple? But
They
they
will
are
not.
show
It
in
will
the
not.
spectrum.
Yes.
Now let us come actually to the first one, that enema spectroscopy is used for determining the structure in which of the materials? Radioactive
Mainly
materials?
liquid.
No. Insoluble chemical compounds, liquids and gases. What do you think?
Mainly liquids.
Mainly liquids, right? Because there is something also known as solid state enemas, right? I have not used it, but uh, the in mostly in liquids it is used for, and that too you have to solubilize in some deuterated solvent. And example of those are CdCl3, DMS or D6. These are mostly used. You have D2O. In BR, actually from BRC we used to buy
Yes.
deuterated
Heavy water
solvent.
board. Actually, heavy water board provides you this. Yeah.
Yes, yes, yes. Then NMR spectroscopy indicates the chemical nature of the dash and the spatial position of what? We are dealing with
The
nuclei and spatial
nuclear and
positions of neighboring
neighboring
group.
group.
Right, not the electrons.
Yes.
A neighboring group will determine what kind of electronic environment does it have.
Yes. It
And
will.
now question number three, that the amount of energy available in the radio frequency radiation is sufficient for which of the following?
The affect the
Excite an
nucleus.
atom, affect the nuclear spin. Because it is radio frequency very, very less. So it will not use in rotational spectroscopy or vibrational spectroscopy or electronic spectroscopy. Right?
Yes.
To excite an atom will require what? Electronic spectroscopy. Vibrate an atom, vibrational spectroscopy.
Yes.
Even vibrate a molecule also.
Yes.
So now let us go to the question number four. Which of the which H of one chloropane two in? So the structure looks like this. First position there is chlorine one, two. There is a in,
Yes.
two. So two, one, three, 4, 5. Pentene means 5 carbons are there. Now they are asking which carbon will have the most which will be most downfilled, or which has the largest chemical shift. What do you think?
Yes.
One, two, three, or four?
Here I have a doubt. In the case of chlorine, it will attract the. And
True.
they, I actually gave. I actually choose option number one, but they provided option number two.
Yes, because this pipe, you can see the double bond is there. So this double bond is actually again cause the downfield of that. You have you have actually learned this in terms of uh, uh, you have learned this in terms of ring current in benzene. So similar kind of effect will be there due to these pi electrons. So they will again be mostly deshielded due to that these pi electrons. So generally, when there is a double bond associated, that proton is again deshielded with respect to the. Uh, so the saturated protons are actually deshielded
Yes.
with respect to the unsaturated protons, I would say. So that's
Yes.
why either C2 or C3, mostly C2. The C2 will be most downshifted because of the chlorine electronegative is there. That point you have already got,
Yes. Yes.
and
Yes.
due to this double bond, this effect of that is going to show up on this second proton. Also, the
Yes.
third proton is the next downfilled one, and then one will come into the place. I guess something like that. But the second proton, this proton is going to be mostly downfilled. These will have the most temperature. Now, question number five. Which of the following statement regarding the NMR spectroscopy is wrong? The first, what is called NMR signal towards the left of the spectral chart corresponding to larger chemical shift. So this is true, right? Left hand NMR.
Yes.
So they
No,
are,
this
tell me,
left shift, larger chemical shift. Yes, yes,
true. They have larger delta value.
yes, yes.
Now, chemical shift are larger when the frequencies of radiation which induces the nuclear transitions are higher. What do you think of this?
This is also correct.
Okay, that is because of the B0, right?
Yeah.
Now, say, similarly, chemical shifts are larger when the shielding effects are greater. If
Fine.
shielding effect is greater, then your proton will be more shielded.
Yes, yes. It is the
So
wrong. Actually, it is
wrong,
the wrong.
right? Because it is
Yes,
going to experience less applied magnetic field.
yes,
So as you already shown from the energies that it is it is it varies as with uh, your B0. So if B0 is less, B effective is less, then
yes,
it is going to be shielded and it will
yes,
be on the right hand side. So chemical sheet will be less.
yes.
Then a hydrogen signal split into n plus 1 peaks by spin-spin coupling when the number of equivalent atom on the adjacent atom is n and no other neighboring atoms are involved. So that's what it is, right? N plus 1
N plus one number. Yes, yes,
and 2n. Why it is not 2ni plus 1? Because I is half for proton. So 2 into half is 1 and n is the number of peaks. If it is carbon, then what would have been? So in place of carbon, also the spin is half. Now
yes,
think of deuterium.
okay.
Suppose we are doing deuterium spectroscopy, not
Yes,
proton NMR, deuterium
yes,
NMR. Then what would
okay,
have happened? How many peaks? Suppose there are two deuteriums are there.
okay.
Then what would you expect? Two.
Then,
So in the adjacent atom, there are two equivalent deuterium.
okay.
Then what will
Yes.
happen?
Then and two splitting will means in case of a like A2 system. You are talking about like
No,
A2
no,
system.
no. I am talking about suppose in case of suppose CD. So suppose this is my molecule,
Okay.
and I am looking at 2D NMR.
Okay.
Not, I mean 2D means not two dimensional. I am saying about deuterium NMR because it is active. I told you the I
Yes.
is
Yes.
one.
Yes.
Suppose I am looking at not proton NMR but deuterium NMR.
Yes.
Then what kind of splitting would you expect for this, this, and this is labile as we have talked. We will not discuss about this. What we will expect for this? So how many in adjacent atom? How many equivalent deuteriums are there? Two. So
Two.
for
Two.
this, we expect two into two, and now I is one.
Okay. Two. Yes.
So you are
Plus.
going to expect splitting of five pentate.
Okay. Five. Okay.
And when you look at this, there are three D are there, so you are getting two into three into one plus so seven splitting will be there.
Okay.
N plus one because two into n into half proton.
Okay.
Right? That's
Okay.
what I am saying. Nothing else. In case of
Okay.
proton NMR, you are going to see this like that.
Okay. Yes. Yes.
So, so it actually follows a Pascal triangle. So that is what I was saying about this AX2 kind of a thing. So for A, you are going AX2 kind of a thing. You are going to see a triplet,
Yes. Yes.
but X2 because they are A2 kind of X, so they are X2 kind of sister. So they will couple with each other, but that will not shown in the spectrum.
Yes.
So
Yes.
they will itself be doublet due to A.
Yes.
So get my point.
Yes. Yes. Yes.
So so in whatever we are discussing, CH3, CH2OH, that is a A3 X2 suppose y, but y is labile. Let us not. So this is kind of a system we are discussing for ethanol. A3 because H3, right? H2
Ye-
because X2.
Yes, yes, atheist, yes.
So something like this. So
Yes,
that is what I was saying. So suppose you have, so the chloropentene we are discussing, right?
yes.
Let us, so what kind of splitting you expect for this? Here two H are there. Here one H
Yes,
is there. So you are expecting a triplet for this, but then again this will split the triplet into either triplet of doublet or doublet of triplet. So that you have to see.
okay.
You are getting my point. They are not equivalent. Both. So it also
This is
going to
different from
couple
this.
with, yes.
Yes,
So they are going to split it into three signals.
yes,
But again, again another proton is there on the adjacent one. So it is going to split this into whatever three will be there. Three will be three into three and three or doublet of triplet. So that I'm not sure what we are going to get. We have to see,
yes.
but that's how it is going to be.
Yes.
And that so far we have only discussed about the fast order spectra. What is fast order NMR spectra? That we are using a large value of magnetic field so that your nu and A and X are separated,
Yes, yes.
and these coupling are not going to coincide with each other. That splitting of A and splitting of X. If that happens, then it would be very
Mm,
complicated. So that will
yes.
lead to second order spectra. And
Mm,
right now we are discussing the first order spectra where we are using a high value of magnetic field, and because
mm.
of which they are well separated and we can see better. So what do you think? What kind of a NMR spectroscopy will be better? 300, 400, 500, 700, 900? Which is going to be best?
Magnetic means higher the magnetic field, it will better.
Yes. Now you tell me that our chemical shifts in delta scale are going to be different for a 300 and 900, or they are going to be the same.
So the delta is independent of your magnetic field, na? So it will
Right.
not matter. Yes.
So that is going to be the same, but the splitting will be more clear. Right. So you for a beta splitting, can you hear me? Hello.
Yes, sir. Yes, yes, I can hear you,
Yes.
sir. Actually,
Yes.
there is some background noise. Is there? That's why I muted myself.
Okay. Okay.
This
So
procedure is there for this as 14th April is there. Na? So there is
okay.
some
Okay.
processing is there. No problem. I can hear you, sir. I just muted myself.
Okay. Okay. So what I was saying that this so we have discussed this now for, and the other thing that is left is that your different kind of NMRs, right? Different pulsing that unfortunately we are not going to discuss that because the time is also up, and also oh that will need another session, but unfortunately this was the last session we had. So maybe you will be able to do that assignment. I think that is a little tougher one, but I hope you will manage it. Again, if there is any problem, please feel free to reach me. Uh, my mail ID is orkoprabhuchaudhuri@gmail.com. I'll happy to
Yes,
help you. Uh, um, uh, so you can you can see my name here. So there will not be any space. The name
okay.
and @gmail.com. So it is easy. So please feel free to reach me if you have any problem with solving the assignment there, and if any other queries also if you have, please feel free to reach me. I hope
Sure.
this session was helpful to you,
Yes, yes.
and with that we'll stop it maybe for today. um, and I thank you for attending all the sessions. I am grateful to you. And
Actually, I am actually grateful to you.
yeah, yeah. It's a mutual thing, but it is encouraging when one joins. So you have the I would say, you have the potential. You think that yes, I have to prepare myself. Someone will be there to attend, and you need to defend that, right? So it was actually mutual. In your case, it was helpful. My case, it was also helpful. So maybe we'll in someday in future we'll cross our path. We'll meet
Yes, yes,
someday, sure, right?
yes,
So with that, maybe we can finish this session, and please feel free to reach me if you have any doubt. Okay,
sure.
Ramitra?
Okay.
Nice
Thank
to
you.
meet you. Hope we'll meet soon. Thank you for
Sure.
joining.
Thank you. Thank you. Thank you.
Yes,
Good
yes.
night.
Good night. Good night. Good luck.